morning friends. In chapter 13 kinetic theory, already we discussed about the wet translational kinetic energy of molecule of a gas is directly proportional to its absolute temperature. That means the average half mv square is equal to 3 by 2 kBT. And after that, we also discussed about the law of equipartition of energy. That means the energy associated with each possible independent motion is half kBT. So that is the law of equipartition of energy. After that, we are going to discuss about what is the degrees of freedom. That is the important thing for our MCQ type question and also in numerical. So how many degrees of freedom possessed by each type of the gas? We know that all the gases are not same. Some gases are made from the single molecule, some of double molecule, that means the diatomic, right? Okay. For that purpose, the diatomic gases are also perform the different type of the motion, Some diatomic gas act as a rigid rotator. That means its both molecules are always combined with each other. While in other diatomic gas, it is made up of the double molecule of gas. But here, these two molecules are independent. That means not depends on each other. That means the non-rigid. So we are going to discuss about what is the degree of freedom, and we have to calculate the degree of freedom for diatomic gas. For that purpose, first the definition of what is the degree of freedom. The number of independent motion possessed by the molecule of a gas is known as the degree of freedom. If the gas is made up of the single molecule, that means all the molecules are separate. At that time, this molecule only possesses the single motion, that is the linear motion. The molecule of a gas perform the random motion. That means in each direction it travels till it not suffers any collision. When it suffers the collision, so its direction of motion is changed. But here this motion is only the linear motion, that means the motion on a straight line. In that case, it has only the three possibility of its motion, either along the x direction, or along the y direction, or along the z direction. Therefore, the three independent motion possessed by this type of the molecule of a gas. So in that case, this molecule of a gas has only three independent motion. Therefore, this gas has the 3 degree of freedom according to its linear motion or translational motion. Okay, now again the definition of degree of freedom. The number of independent motion possessed by molecule of a gas is known as the degree of freedom. How many possible independent motion for a given gas? That is known as its degree of freedom. Again we repeat the definition. The number of independent motion possessed by molecule of a gas is known as degree of freedom. Thus, the possible independent motion, or in other words, degree of freedom, depends on the following factor. First is the molecule is made up of how many atoms? How many atoms? Some molecules are made by the single atom, some by 2 atoms. That means the diatomic molecule. And single atomic, only the monoatomic molecule. Okay. So degree of freedom depends on molecule is made up of how many atoms. And second, it depends on the temperature of a gas. Again, keep in mind that the degree of freedom depends on the 2 factors. One is the molecule is made up of how many atoms, and second, the temperature of a gas. Clear this thing? So that is the definition of the degree of freedom, and also on which factor the degree of freedom depends. After that, we are going to calculate the degree of freedom for diatomic gas. First thing, which gases are the diatomic gases? The diatomic gas like oxygen, nitrogen, hydrogen or CO have the three linear degree of freedom. Again, we are going to calculate the degree of freedom of diatomic gas. The diatomic gas like O2, N2, H2, CO, etc. Now this gas has the three linear degree of freedom. Three linear degree of freedom corresponding to its linear motion along x direction, y direction and z direction. Therefore, the total energy or the total translational energy Et is equal to average half mvx square plus average half mvy square plus average half mvz square. So these three independent linear motion produced by this type of the diatomic gas. So corresponding to its linear or the translational motion, it has the three degree of freedom. Clear this? Okay. Now, it can also produce, that means the oxygen. We consider for the example, oxygen is the diatomic gas. The molecule of the oxygen first perform the linear motion. According to its linear motion, its total energy, that is the E translational, is in three terms. Therefore, it has the three degree of freedom. Now, it can also produce the 2 degree of freedom according to the rotational motion. Here the molecule of the oxygen is made up of 2 atoms. These 2 atoms are separated by the finite distance. So this diatomic molecule of oxygen produces the linear motion plus rotational motion as shown in figure. Here there is the one rotational motion according to this way. Here the molecule of the oxygen performs the rotational motion about the axis perpendicular to these two, like to this way. Here there is the white chalk is the axis and green chalk is the distance between the 2 atoms of the 2 molecules of oxygen. These 2 atoms perform the rotational motion about this vertical axis. And second, here the axis of rotation is this. The 2 molecules are like to this way. So it performs the rotational motion like to this way. This way. About this axis. Right? Like to this. So here the 2 different type of the rotational motion produced by the molecule of oxygen gas. For example, O2 molecule, there are the 2 independent rotational motion as shown in figure. If omega 1 and omega 2 are the angular speed about the axis 1 and 2. Suppose here the angular speed is omega 1, here the omega 2. About the axis 1 and 2, and I1 and I2 with the moment of inertia about that axis. Moment of inertia about that axis. Therefore, the kinetic energy, rotational kinetic energy is half I omega square. Already we learned in rotational motion. Therefore, total energy of the molecule E is equal to translational kinetic energy plus rotational kinetic energy. Translational kinetic energy is this: half mvx square plus average half mvy square plus average half mvz square plus 2 terms of the rotational motion or the rotational kinetic energy according to the or the about the axis 1 and 2. There is the half I 1 omega 1 square plus average half I2 omega 2 square. Here the 3 terms of the linear kinetic energy and 2 terms of the rotational kinetic energy, hence the total 5 degree of freedom. Again, the diatomic molecule has the linear kinetic energy for the linear motion. Due to the linear motion, the possibility of independent linear motion are 3 along the x, y and z axis. Therefore, the total translational energy is equal to half mvx square plus half mvy square plus half mvz square. Now, the diatomic gas, like as the oxygen, also possesses the rotational motion. And this rotational motion is about the 2 different axes as shown in the figure. First is the vertical axis and second is about this axis. If the angular frequency of rotational motion about the axis 1 is omega 1 and about the axis 2 is omega 2. And the moment of inertia of a diatomic molecule is I1 and I2, then the total energy of molecule is equal to translational kinetic energy plus rotational kinetic energy. Rotational kinetic energy is, we know the equation half I omega square. So corresponding to this axis, half I1 omega 1 square, and according to this axis, half I2 omega 2 square. Therefore, the total energy of the molecule is equal to average half mvx square plus average half mvy square plus average half mvz square plus 2 terms of the rotational kinetic energy, average half I1 omega 1 square plus average half I2 omega 2 square. Here 3 terms of the linear kinetic energy and plus 2 terms of rotational kinetic energy, hence the total 5 degree of freedom. Now at room temperature, this molecule have the mode of vibration. Here these 2 molecules, 1 and 2, at room temperature oscillate or vibrate about their mean position along the intermolecular axis. That is the intermolecular axis. One molecule is this, second is this. So at room temperature, these 2 molecules are oscillate or vibrate about their mean position. There is the O is the mean position, maximum plus A, this side minus A. So this vibration motion like a one-dimensional oscillator as shown in figure. Therefore, the vibrational energy is equal to kinetic energy plus potential energy. Here the kinetic energy is half m dy by dt square plus half ky square. Actually, there is a half mv square. What is the velocity? Change in displacement with respect to time. Therefore, dy by dt whole square, that is our speed of vibrational motion, plus half ky square, that is the potential energy. So here also the 2 terms corresponding to its vibrational motion. So therefore the total energy is E is equal to translational energy plus rotational energy plus vibrational energy. Thus they are total 7 terms, hence the degree of freedom are 7 of diatomic gas. Of diatomic gas. So in short, just we discussed about that the degree of freedom depends on the factor the molecule is made up of the how many atoms. Here we consider the example of the diatomic gas. So diatomic gas, the molecule of diatomic gas is made up of the 2 atoms. So as a result, it possesses the 3 different type of the motion. One is the linear, second is rotational, and third is the vibrational motion. corresponding to its linear motion or the translational motion, it has the three independent motion along the x, y, and z. Therefore, the degree of freedom due to the translational or the linear motion is 3. Now, the diatomic molecule of the diatomic gas, like as the oxygen, also perform the rotational motion about the two axes shown in the figure. Therefore, the two terms of the rotational kinetic energy. So it also possesses the rotational kinetic energy or the energy in form of the rotational motion. Now, here it performs the rotational motion as shown in the figure according about the axis 1 and 2. So here the motion is possessed like this way, and here the motion is possessed like this way. Therefore, it has the two rotational kinetic energy. If the omega 1 and omega 2 be the angular frequency of the rotation about the rotational axis 1 and 2, and I1 and I2 be the moment of inertia, therefore the rotational kinetic energy is average half I1 omega 1 square, and about this axis average half I2 omega 2 square. Now the total energy of the diatomic gas is E is equal to translational kinetic energy plus rotational kinetic energy. 3 terms of the translational kinetic energy plus 2 terms of rotational kinetic energy. Okay. Now at the room temperature, here that is the diatomic gas. It has the 2 atoms in one molecule. So these atoms are also vibrate about their mean position at room temperature. Therefore, this molecule also possesses the vibrational energy. So vibrational energy is equal to kinetic energy plus potential energy. Kinetic energy is half m dy by dt square, because the kinetic energy is equal to half mv square. V is equal to change in displacement with respect to time. Therefore, dy by dt. Therefore, half m dy by dt whole square plus half ky square is the potential energy, k is the force constant, and y is the displacement of vibration. Therefore, the total energy of the molecule of a diatomic gas is kinetic energy plus according to the rotational energy plus according to the vibrational energy. So 3 terms corresponding to the translational energy, 2 terms corresponding to the rotational energy plus 2 terms corresponding to the vibrational energy. Therefore, they are the 7 terms. Hence, the diatomic gas has the degrees of freedom are 7. Here we consider that it is a non-rigid rotator. Non-rigid rotator, that means the distance between the 2 atoms is not fixed. Is fixed. Sorry. Here the non-rigid rotator, that means the distance between the 2 atoms forms the one molecule. The distance between the 2 atoms is not fixed, that may be changed. And due to that reason, it possesses the vibrational motion. So for the diatomic gas non-rigid rotator, so there are the total 7 terms of total energy. Therefore, the degrees of freedom are 7. If the diatomic gas we consider as a rigid rotator, that means the distance between the atoms, 2 atoms of the one molecule is fixed. At that time, the vibrational motion does not take place. Only the linear and rotational motion take place. For which gas? Diatomic gas with rigid rotator. Rigid rotator, that means the distance between the 2 atoms is fixed, does not change. Therefore, the vibrational motion does not take place. Only the linear and also the rotational motion take place. So in that case, the degrees of freedom are only 5. 3 corresponding to the linear motion and 2 corresponding to the rotational motion. Clear this? Diatomic gas non-rigid, the degrees of freedom are 7. And diatomic gas with rigid rotator, degrees of freedom are 5. And simple gas, that means the molecule of a gas made up of only single atom, it has only the three different type of the linear motion along the x, y and z axis. Therefore, three independent motion. Therefore, the degree of freedom for the monoatomic gas is only 3. Clear it? Okay.